I'd like to do another example of a quantum mechanics calculation using bra-ket formalism and the matrix representation of operators. In particular, what I'd like to do, I'd like to consider the lowering operator for angular momentum. Remember, that's this operator if we're in the Jm angular momentum state. That's J labeling the total angular momentum quantum state and M labeling the Z component of angular momentum state. If we're in that state, remember the lowering operator J minus takes us to J comma M minus 1. The M minus 1 state goes down by 1, and some constant out front. We derived this in the book or in class. We are not going to go through it in gory detail. I just want to practice asking, how do I get from that to a matrix representation of that for a particular set of states? Specifically, let's look at the spin-1 states, and we want to know what is the matrix representation of this operator as applied to those spin-1 states. And eventually, where we're going with this, I want to take it in the direction and ask, what are the Jy eigenstates? We'll get to that in a bit. But first, spin-1. Want to do this. So let me just look at this. I have here the standard form for the matrix representation of a quantum mechanical operator in the SZ basis, which is what these kets 1, 1, 1, 1, 1, 0, 1 minus 1, those kets and bras are all in that basis. Here's what we do. We have to define the matrix representation. We basically sandwich the operator we care about in between successive pairs of bras and kets in the basis. And this is a standard form. You just list your basis going down. Each column has the bras going basis elements 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. Each row has the kets in the basis element 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. We're just extracting the term for each one that corresponds to that bra and that ket. We're looking at that overlap between those things. That's what this matrix representation tells us. So to do that, we're going to need to figure out how to evaluate each one of these brackets into a number, because that's the whole point. We always want to evaluate these things into some kind of an actual number. Fortunately, we've got this equation up here for how J minus acts on kets that we can use to do that. So let's go through and figure out, in the 3 kets of our basis, let's figure out what that action is, and we'll go and have a look at what we do. So we'll start with just the 3 kets in a row. J minus acting on 1, 1. Acting on that, I can just use this definition. That's going to be equal to the square root of 1 times 2, 1 times 1 plus 1, minus M is 1, so 1 times 0, times h bar times 1 comma 0, or in other words, the square root of 2 h bar times the 1, 0 state. So this is what we expected. J minus acting on 1, 1 lowers this m value by 1 and gives us some numerical coefficient out front. We can do the same thing with the others. J minus acting on 1, 0 will give us, let's do the same thing. We get the square root of, let's see, same thing up front, 1 times 2 minus, and now 0. Oh, 0. We're done there. Times h bar times 1 comma minus 1, because we're lowering. So in other words, that's once again square root of 2 h bar 1 comma minus 1. That's our lowered state. And finally, more or less by definition, we know, well, by earlier arguments, we know that trying to lower the lowest possible state is 0. You can confirm it by plugging in the numbers as well, but this comes out to 0. You can't lower below the lowest possible state. So we know these 3 values. We know what J minus does to each of these kets. That means we can evaluate what happens in this matrix. And we can just come right over here and just say this matrix is going to be equal to, well, I'll go ahead and write it out again just so we can see it. The matrix is going to be equal. My bras are going to stay the same because I'm just acting on kets the way we're setting this up. So my bras in each one of these will be 1, 1, 1, 0, and 1 minus 1 are those 3 bras. And then J minus on 1, 1, I know what that is. That's the square root of 2 h bar times the 1, 0 state. And this is the square root of 2 h bar times the 1, 0 state. And this is the same, because that's all the same state here. The row, the whole column rather, the whole column is exactly the same. So I've got that going. And then next one, I can do the same thing. 1, 1, 1, 0, 1, minus 1. And here, j minus acting on 1, 0 gives me square root of 2 h bar times the ket 1 minus 1. Here, square root of 2 h bar times 1 minus 1. And here, square root of 2 h bar times 1 minus 1. Now, if you're good at this already, you could probably skip a lot of these steps. If you're already really skilled at this, you know where this is going. You don't need to write this all out in great detail. It looks like I'm tending down there. I'll try to fix that. My final thing, I'm not going to write it all out because I know j minus applied to the final column is going to give me zeros everywhere. So that's just going to be 0, 0, and 0 for my final column. And I've got all that. So okay, this is just using my known action of j minus on the states and plugging it into the definition of what the matrix representation is. Straightforward enough. If you know what the operator does, you can do things. Now we still have all these bras and kets, all these brackets to analyze. Remember that all of the constants here, the square root of 2h bar that shows up all over the place, all of those are just constants and can factor out of the bracket. We can leave them out entirely. So imagine those are factored out. We now say, hey, the 1, 1, 1, 0, and 1 minus 1 states are an orthonormal basis for the space of states. That means that in particular, there is zero overlap between 1, 1 and 1, 0. The bracket of 1, 1 with 1, 0 comes out to be 0. So if I wanted to evaluate this, I'll just do this. If I wanted to evaluate this matrix and evaluate each one of these, I can now evaluate those brackets. I'll find 1, 1 with 1, 0, that's just 0. 1, 0 with 1, 0, these are normalized states, normalized basis states, so that's equal to 1. So 1 times square root of 2 h bar is that. 1 minus 1 with 1, 0 with constants, that's 0. So put some commas in here. Next column, 1, 1 with 1 minus 1, nothing. 1, 0 with 1 minus 1, nothing. 1 minus 1 with 1 minus 1, that's a normalized state, so it's equal to 1. We get square root of 2 h bar, comma, 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 and these are still all 0. We now have our matrix representation of this state. And often we'll end up factoring out the h bar at least, maybe the whole thing. We could write this as h bar square root of 2 times 0, 0, 0, 1, 0, 0, 0, 1, 0. And if you wanted to write it that way, you can make it, sorry for squeezing it against the side here, you can make it a very efficient little presentation, factoring out all the complicated stuff. Don't know why I reversed the order there, but whatever. You've got this. We've found now the matrix representation of the j minus state, of the j minus operator, rather. So that's how you do these things. To find a matrix representation, you need to know how your operator acts on the kets, how it acts on the states, and then you need to just know the overlap between your kets and your bras in your given basis, which should just be a standard orthonormal basis overlap for most cases. And you can put it together to find this representation. There we have it. That is the representation of the Spin-1 lowering operator matrix in the SZ basis. Now, I want to take a minute, since this is only a piece of this, I want to take a minute to use this for something useful. I'll copy this down, just so I have it up here. I'll copy that down, and what I want to do, I want to go ahead and interpret this. I want to interpret this to give me what the SY, or rather JY, angular momentum matrix representation is for the actual X and we'll look at Y for the components along something other than the Z basis. How do I find the operator representation, the matrix representation of the operator for angular momentum around the X basis or the Y basis? Well, I'll copy this down. As I said, I know that J minus is represented in the SZ basis by h bar times the square root of 2 times 0, 0, 0, 1, 0, 0, 0, 1, 0. We know that J plus from work earlier is equal to J minus dagger, the adjoint of J minus. In matrix form, that's just a conjugate transpose, and hey, there aren't even any imaginary numbers here, so that means that this in the SZ basis, that's an SZ really it is h bar square root of 2. The transpose of this is just 0, 1, 0, 0, 0, 1, 0, 0, 0. we've got all those pieces together. And so I know J plus and J minus. This is the great part where we can look at the original definitions of J plus and J minus, again, referring back to the derivation we made of the angular momentum states in the JZ basis. If we go back to the original definition of these raising and lowering operators, we remember that J plus or minus was defined to be Jx plus or minus I Jy. So if I wanted to know Jy, if I can just solve these two equations for Jy, essentially, I'll find that Jy is equal to, well, if I subtract the two, if I do J plus minus J minus, that'll give me 2I Jy, so I have to divide by 2I, 1 over 2I, times that difference. Hey, that means I know what those are. I can just very easily write up my matrix representation of this in the SZ basis. 1 over 2I times this thing. I can write as the 1 over I is a minus I. I can write this then as I'll have the h bar outside, and square root of 2 over 2, I'll write as h bar over square root of 2 because I don't care about rationalizing my denominators. I've got this, and I'll have 0 minus I 0, I 0 minus I 0, I 0, and that's my Jy representation. That's going from knowing what J plus and minus were, knowing those matrix representations, I'm able to figure out what the Jy representation is from that, just working straight from what we knew about J plus and J minus. Again, this is just from the derivation, we're deriving this from what we found in class or what we found in the textbook about how these relationships work. What does J minus do to the states? Knowing that was enough to tell us this representation for the Y component of angular momentum. All right, so the final thing I want to do, now that we've got that, we may as well just ask, let's figure out what the eigenstates of Jy are in this JZ basis. No, I'm calling it the SZ basis. Okay, so I'm obviously being a little bit glib about the equivalence between spin and total angular momentum. SZ, JZ, same deal. We'll worry about that later. So what I want to do is I want to figure out what are the eigenstates of this. What are the Jy eigenstates? And this is where most people, or a lot of people anyway, will look at this and say, oh, it's a matrix. I know how to find the eigenvalues and eigenvectors of a matrix. I'm going to do that. Which is a great idea. I love finding eigenvectors and eigenvalues. It's great. Don't plunge right ahead, though. Don't plunge straight into doing the calculation, because here's the thing. We already know what the eigenvalues have to be. You don't need to do a big determinant of all. You can. More power to you. You know, do your determinant, find what the eigenvalues are, but I know the answer already, and honestly, so do you. The answer is the eigenvalues, hope this color is showing up, are going to be h bar, 0, and minus h bar. The same ones that they have for the JZ, or that we had for the Z component of angular momentum earlier, and for any other component, because it's just symmetric. This, physics doesn't care whether we're looking at x or y or z. Physics just cares about what those eigenvalues of angular momentum are along a given axis. We know it has to come out to be these same three values. It has to. So if you want to check that, by all means, find your eigenvalues of this matrix by doing the big ugly determinant. You're welcome to do it, but we already know. In general, if you can ever guess or know the eigenvalues of a matrix, it cannot cause you any harm to just assume them, to just go with that, rather than deriving them from scratch. You save yourself so much time and effort if you can guess the eigenvalues. Even if you only guess half the eigenvalues, that makes it easier to find the other half. So, okay, we know the eigenvalues. That means that we can find the eigenvectors. And in the interest of time, let's just look at a single one. What is the minus h bar eigenvector? What will be the minus h bar eigenvector for the Jy operator? In other words, what I want to know is, I want to know the 1 minus 1 y basis ket. I want to know what that is in my, I'll keep calling it SZ even though that's confusing. I want to know what is that in my z basis, in my z component of angular momentum basis, what is this 1 minus 1 ket, the minus h bar eigenvector of this matrix? Well, hey, if I know the eigenvalue already, I can just write down what the definition of an eigenvector is. I can just say that this matrix, I can say h bar over square root of 2 times 0 minus I 0, 0, oh, not 0, I 0 minus I 0, I 0 times some vector. I'm going to give it a really boring label. I'll just call the components A, B, and C, has to equal the eigenvalue minus h bar times the same vector, A, B, and C. And that's the definition of an eigenvector. And we can use that. That gives me 3 equations that I can use. Now, we know they're going to be redundant equations. That's what we did to find this eigenvector thing in the first place, was to make these redundant equations. So we know only 2 out of 3 are going to be independent. But we'll see what we got. So let me clear some space over here to do that calculation. If I look at those equations, first of all, h bars cancel out. Thank goodness. Don't need to worry about h bars. So looking at this equation, the first row will give me that minus I over square root of 2b, that's this product here, first row, minus I over square root of 2 times my b coefficient equals minus a. That's it. We cancel out the h bar, but I still have the minus out front, so that it becomes minus a. My next row gives me I over square root of 2a minus I over square root of 2c equals minus b, and the third one gives me plus I over square root of 2c, no, b, sorry, I over square root of 2b equals minus c. All right, so looking at this, standard thing, I want to put these all in terms of a, just to choose one of them as the one I'm going to keep as my leftover parameter. There will always be one for an eigenvalue eigenvector problem like this. There will always be one free parameter left. And the 2 equations that are easiest to work with pretty clearly going to be this guy and this guy. So what do I have? I have that b equals minus I square root of 2a, and I have that c equals, let's see, if I just compare these two, they're opposite, so c equals minus a. So in other words, my vector a, b, c has to equal, what do I have? A stays the same, a and then minus I square root of 2a, and then minus a is my vector. That's the general form of an eigenvector of this matrix with eigenvalue minus h bar. The last thing I need to do is normalize that. I need to normalize this vector, and so what is this? The norm of this thing, what do I want to call this? If I just give this a name, if this is v, then the norm v star v has to equal, well, it'll be the absolute value of a squared for the first one plus the absolute value of minus I square root of 2a squared for the second one plus the absolute value of minus a squared for the third one. That comes out to be just an a squared, absolute value of a squared, times 1 plus 2 plus 1, or in other words, essentially, this comes out to be 4 absolute value of a squared, and I know that norm has to equal 1. The whole thing has to equal 1 to be a normalized state. So finally, I can figure out, for simplicity, I'm just going to keep a nice real number thing, none of this complex business. I'm going to take a to equal 1/2, and that'll do the whole job. So in other words, my h minus eigenvector, if I want to write it down, where can I write this down? I'll keep that there. We've already used this up here. I'll put it up here just to have it here. So that means that my 1 minus 1 y in the z component basis looks like, remember I said a equals 1/2, is a good enough answer. And so I'm going to represent this as, well, I'll factor out the 1/2. Why not? I'll write it as 1/2 times 1 minus I squared of 2 minus 1. And you can check that's a normalized vector, and it works just fine. Or in other words, 1 minus 1 in the y basis is equal to 1/2 times, that's my coefficient for the 1, 1 in the z basis, the default z basis, minus I squared of 2 over 2 times 1, 0 in the z basis, minus 1/2 times the 1 minus 1 state. And that is my final state. So what did I do here? I found, we've gotten what the y basis state is. We found the y eigenstate here for the minus h bar and the y component of angular momentum. And we've written it in terms of the z states by doing this matrix problem, by calculating some eigenvalues and eigenvectors. And it's kind of neat that we can do this. Remember, we started from just the equation we had for how J minus acted on states. And we were able to extend that into all this thing. We were able to extend that to figure out what are the Jy eigenvectors and eigenstates. We could do the same thing for the 0 and the plus h bar eigenstates as well, or eigenvalues as well, if we really wanted to. But you get the idea of it, I hope, that once you've got your matrix, don't recalculate the eigenvalues if you don't have to. Once you've got the matrix, go with an eigenvalue that you know and calculate the vector that comes with it. With that, that's the end of this example, and we'll do more in the future.